So thanks again. I'm Rémi Bardenet, so I'm from Lille. My research is actually not what I'm going to present. So I chose to give a mini course. I chose to take this opportunity to give a mini course on an overview of Bayesian learning. I understood the mission as that. My own research is actually on repulsive point processes, as Pierre said. So repulsive point processes, ways to draw points on in RD such that no two points fall too close to each other. And I use this to try to come up with Monte Carlo methods that are provably better than IID or any other classical Monte Carlo method. But that's not what I'm going to talk about today. So I'm not going to talk about Monte Carlo methods. I'm going to talk about Bayesian learning. It's going to be a very simple tutorial today and tomorrow, maybe even more today. So I'm going to try to say very simple stuff in a very complicated manner, but this is part of my own effort to try to go back to the roots of being Bayesian and try to understand why I'm Bayesian and if I still want to be Bayesian. And let's try and instill doubt in every one of you at the very beginning of the week. I thought it might be good to instill doubt about being Bayesian as the very first talk of this week. I'm going to cut the lecture in 3 parts. So there's going to be what, why, and how. So what is being Bayesian? What is Bayesian learning? That's every researcher in the room is probably going to follow this very easily, and you can email during that first part. It's fine. This is more for people who are more newcomers to the field, or people who are being Bayesian because they've been taught to be Bayesian, which was basically me in first year of PhD. I mean, it's being Bayesian is what your advisor is, and you're attacking the problem in a Bayesian way, and then you try to validate for yourself the fact that you're attacking the problem in a Bayesian way. And then I took this path of trying to convince myself that it was still the best thing to do for the next 40 years of my life. So let's see. So I'll start with what. Probably at the end of today, I'll be in the middle of why. So why would you want to be Bayesian? So there's several arguments in favor of being Bayesian when you face a learning problem. Not all these arguments are compatible with each other. So you need to choose a set of these arguments. You cannot take all of them. Not all of them give you the same degrees of freedom in picking up priors, likelihoods, generalized likelihoods. So during the course of this week, if I believe the schedule that I've seen online, you'll see several types of Bayesian come here at my place, and not all of them will be compatible in terms of philosophy. So I'll try to insist on this. This is going to be the why part of the talk. And then the last part of the talk is going to be the how to be a Bayesian, so how to actually implement the principle of expected utility that we're going to cover in this first part. And this is going to be the realm of Monte Carlo methods, and then probably half of the talks of this week are actually concerned more with the how than the why or the what of being Bayesian. So let's start. Just to be sure we're on the same page, I'm not speaking of this Bayesian. So I don't know if you've Googled Bayesian bodybuilding already, but that exists. And this guy is the inventor. And he gives courses. So if you look for Bayesian training, you actually fall quite early onto the webpage of that guy. So he's a Dutch bodybuilder. Don't know if he makes Dutch books, but he's a Dutch bodybuilder. And he sells courses on Bayesian bodybuilding. And Bayesian bodybuilding, Bayesian is basically a keyword for which means science-based. So there's nothing really more statsy than this, right? It's science-based. So I'm going to teach you the science of nutrition and the science of training, and then you'll be super fit like me. And that's being Bayesian. So being Bayesian is trendy. So that was the funny part, but the less funny part, the more serious part, is that being Bayesian, like the keyword Bayesian is so trendy at the moment that it's starting to be taken by pop culture as a token of science-based. I think that's kind of funny because big data has been there's already a pop band called Big Data, and now there's a bodybuilder called Bayesian Bodybuilder. So I think it's a good sign for Bayesian stats actually that people start thinking of the word Bayesian as a cool name that you can adapt to your brand. Okay, this is more the kind of Bayesian stats or learning that I have in mind. This is a paper. I don't know if you've heard about this, but we have this. We have LIGO and Virgo, two giant interferometers, one in Italy and one in two sites in the United States. Two giant interferometers that are dedicated to the detection of gravitational waves. And this is the paper that announced the first official detection of a gravitational wave event. And I was really happy with this paper, not only because we've detected gravitational waves, which is a cool fact, but also because if you look at it, the paper is entirely Bayesian. If you look at if you look at this mention, for example, so they cite the inferred masses of the initial black holes are these two values at the 90% credible level. So they give you credible intervals in the abstract. So that's a Bayesian measure of uncertainty for those of you who haven't met that. 90% credible region. There's even Bayes factors in this paper. So it's really satisfying, and there's absolutely no mention of a frequentist measure of uncertainty in this abstract, which is, I think, a good sign that Bayesian stats and the Bayesian way of thinking is actually being taken seriously by at least some scientists, and the fact that being Bayesian cannot lead to scientific consensus, I think, is past us, at least in some areas of science. Astrophysicists, cosmologists, for example, are very keen on being Bayesian. I think probably because there's not much sense in imagining a large number of repetitions of their experiments. They have one gravitational wave event, and they have to deal with this. Oops, sorry. This is just another passage of the paper. You can see they're even inferring the direction of the event, and they're showing you credible regions on the sphere and updates, blah blah blah. If you look at the caption, the full Bayesian localization is shown in purple. I think that's quite interesting to have this in physics paper. This is also the kind of Bayesian learning I want to talk today. This is more machine learning than statsy. So this is a classic paper by Hoffman, Bly, Wang, and Paisley, introducing stochastic variational inference. And basically, they did topic modeling. So they extracted topics automatically from a large collection of text, of documents. And you can see that they are able to treat data sets of the size of 3.8 million articles from Wikipedia. The fact that we can apply complex Bayesian models to massive data sets is also something that's becoming more and more common, especially thanks to variational inference. That's something that we'll cover in the how part of the talk. But I think this is also a good sign that I wanted to show in the introduction. There's physics papers that are entirely Bayesian, so that's good. The scientific pipeline is adopting a Bayesian view. The Food and Drugs Administration has a whole webpage on recommendation for Bayesian methods. And you see machine learning papers with Bayesian methods being applied to real life data sets like collection of texts the size of Wikipedia. Okay, this is going to be the outline of today's talk. So I'm going to give you, this is going to be still an introduction, this data-driven definition. I'm going to try to define what Bayesian machine learning is using data, and you'll see what I mean. Then this is going to be the very 101 part. So I'm just going to recover with you like estimation and regression models, different ways to estimate the parameter of a linear regression, just to come up with the right notions, to come up with the notions of decision theory that we need to introduce machine learning as data-driven decision making. Part 4 is really the core of what being Bayesian means. It's subjective expected utility. And once we've stated this principle in all generality, we'll revisit a couple of examples that I will have introduced along the way, and we'll see how to derive a Bayesian decision in the simplest cases. So regression, classification, clustering, whatnot. Okay? Okay, data-driven definition. I can still stand up because there's not much to note at this point. So when I wanted to define what Bayesian machine learning was, I thought, okay, let's look at what data tells us. If you look at NeurIPS is a big conference in machine learning. I don't know if you know it, but it's one of the two, say, major conferences. And I took all the NeurIPS abstracts up until 2016, because I first looked at this in 2017. I took all the abstracts. I downloaded all the abstracts automatically. And then I looked in all these abstracts. There's maybe 1,000 abstracts in there. No, there's actually 1,000 that contain the keyword Bayesian or Monte Carlo or anything that's definitely anything that, no, actually not Monte Carlo, actually keyword Bayesian. So there's 1,000 papers in NIPS up until 2016 that contain the word Bayesian in the abstract. And if you look at the left plot, they're shown in red. So by year, you have the proportion. So the number, the red bars are the number of papers at NIPS mentioning Bayesian in the abstract and not mentioning Bayesian networks, because Bayesian networks is a bit confusing. It could be a frequencies paper about Bayesian networks. So I removed them. So these are for sure Bayesian. You can see this steady linear increase of the red part, and the blue bars are actually the number of papers at NeurIPS. Obviously, the number of papers in machine learning is exploding. It was exploding already in 2016, and it's continuing to explode. But the Bayesian papers are not responsible for this explosion. Okay, the Bayesian papers are in steady. I mean, it's a steady increase. I would bet on such a field. If you look at neural net, for example, that's the second panel. You can see that it was very popular in the 90s, and then there was the famous neural net winter between 2000 and 2010. Sorry, doesn't recognize my face. So there was this famous neural net winter between 2000 and 2010, and then the neural nets came back with the coming of deep nets, 2010, and you can see that it's starting its exponential increase. And this is the kind of topics that's responsible for the exponential increase in the number of papers, as you can see. But still, NeurIPS is about 10 to 15% of the papers at NeurIPS, so it's a steady trend. Now, if you look at these papers, if you look at these abstracts, and I tried to be Bayesian about it, about trying to understand what Bayesian is. So I ran a topic model on these abstracts to try to identify topics in the Bayesian abstracts on NeurIPS. So try to understand what NeurIPS told me what Bayesian learning was. And if I run a model, stochastic variational inference, so the method presented in the paper that I was showing you earlier, on a model called latent Dirichlet allocation, which we'll probably have time to cover a bit in detail, probably tomorrow. This is what it spits out. So these are the 10 topics that it found in my collection of abstracts. So I asked it to find 10 topics. These are the 10 topics. You can see that, and the topics are shown here as collection of words. So one line is a topic. You can see the green topic is about models and non-parametric inference. You can see a Dirichlet. You can imagine Dirichlet processes. You see hierarchical non-parametric models. So that's definitely a modeling topic. You have a computing topic in blue, inference, Monte Carlo, Markov sampling, variational time algorithm, and CMC approximate. That's the computing. So there's a topic. There are a couple of papers that use these words a lot. Then you have a regression topic, Bayesian Gaussian prior regression, estimation likelihood sparse, parameters matrix. That's the regression topic, right? So there's also papers that talk about regression in Bayesian stats, in Bayesian machine learning. And you've got a couple of other topics as well. So you could imagine like building a course by calling it, okay, these are the 10 parts of the course, and let's try to do a course on Bayesian machine learning. So that's Bayesian machine learning from a machine point of view. Now let me tell you the story differently, like the way, maybe more the way it is taught in a book like Christian Robert's 2007 book, if you've read it. And it starts with estimation. So that's going to be my warm-up. This is where I'm going to introduce most of the notions. I'm going to use graphical models quite a lot. So who knows probabilistic graphical models? All right, about half. Okay. So it's a way to represent the dependencies in a joint distribution, okay, using a graph, a directed graph. A graph is a set of edges. Oops. A graph is a set of edges and a set of vertices, okay? And the edges are directed here. And the way you encode the dependencies in a joint distribution is you represent one node per variable in your state S. Say I want to represent an estimation framework where I draw IID data. I will draw one node per datum and one node for the parameter theta. This here, if I use property 1 above, property 1 tells me that this graph is equivalent to the following factorization, P of y1n. I will always use this MATLAB notation to denote y1 up to yn. The joint of y1n and theta. So by this is Bayes' theorem. This is nothing new. I'm not using 1 yet, but where I'm using 1 is here. So this is the product for I equals 1 to n of P of yi given theta. Okay, this is the way these graphs encode dependencies by equation 1. P of S is the product over all vertices, the product over all variables of P of S given its parents in the graph. So P of theta, then P of y1 given its parents, its only parent is theta. P of y2 given its only parent, again theta. P of y3 given its only parent, theta again. Okay? Let me give you a second example. Well, first, let me introduce a plate notation. So I'm gonna use this plate notation also. So I'm just drawing a square around the node yi, and I'm noting here that there's n of them. And this is just equivalent to the notation on the left. So just imagine that a plate is here for repetition of a particular node, and you copy all the edges that cross the border of the square of the plate. Okay? So I don't know, to give you another example, imagine you have a hierarchical model and you have two classes, theta 1 and theta 2. Maybe you are fitting the height of a group of people and you want to separate them between, I know, men and women. You think there's a common prior about the height of a human, but then you think that there's a theta m parameter and that the height of men here. So let me draw a plate. They're drawn IID conditional on theta m, and you have the height of women drawn IID conditional on theta women. Okay, that's another probabilistic graphical model, and the factorization that goes with this is the following. So there's again P of theta. There's P of theta m given its only parent theta, P of theta women given its only parent theta, and this is IID, the product over I equals 1 to, so here I have the same number of men and women. I could actually have different numbers, number of men, P of yi men given theta men, and the product for n women of P of yi, P of yi women given theta women. Okay, this is the factorization that this graph corresponds to. Okay, every graph is just a way of representing the conditional dependencies in a joint distribution. And usually in machine learning, this is how you specify a model. You specify its dependency structure, and then you define the arrows. And the arrows are the actual conditional distributions. Okay. That being said, let us do a regression model. Okay, who knows this guy? Yeah, this is Fischer. Apparently the single nicest guy in the history of statistics. He was not very nice, apparently. So Fischer, first half of the 20th century. Let's try to do a regression with him. So let's say y is equal to x theta plus epsilon. Y is in r to the n. Or let me keep a capital N for the number of observations. And theta is the parameter of interest. It's in RD. And epsilon, oops, I have to deactivate this. And epsilon is a Gaussian, let's say with identity covariance matrix. So how would Fischer tell us to actually do inference on theta here? Fischer would say, do maximum likelihood in any situation. So Fischer would probably say, theta hat MLE, you should define it as the R max of your likelihood, or equivalently your log likelihood, and this is going to be proportional to this. Right? And you know the solution to this, at least if X is full rank. This is the solution. You can also prove that theta MLE is unbiased. So it's actually, its mean is the actual theta, and its covariance matrix has this form. So the more, whoops, I should probably put a sigma squared here. So the more noise you have, the more noisy theta hat is, but the more data you have, the less uncertainty you have on this theta hat MLE. So that's how Fischer would quantify the uncertainty on theta hat MLE as well. He would give you the sampling distribution of this theta hat MLE, and you would use this to derive confidence regions. Right? This is frequentist statistics 101. Then, that's what Fischer says. Then comes this other guy. Who knows who this guy is? That's a tough one, but this guy really deserves to be known. This is Wald. Wald, I think, dies in 1950. He came up with statistical decision theory. So this is pretty much the theoretical framework of machine learning and statistics today, at least Bayesian statistics. It's his book, his 1950 book, was very influential. And Wald would come and say, oh no, this is not the way to do frequentist statistics. What you should do is you should, if you want to estimate a parameter theta in linear regression, is you should have a loss function. You should have a loss function. Your loss function could be, for example, theta minus theta hat squared. Okay, but that's a choice. That's something that you enforce. So you decide that when you predict theta hat for theta, you suffer theta minus theta hat squared. And then Wald says the important quantity is the expectation of this loss under the data generating distribution. So here that would be under y given x and theta. The problem is this here is a function of theta. It's a function of theta hat, that's fine. I'm going to denote it by RW for risk Wald. So the risk function here is a function of theta. and theta hat. Theta hat is fine. At some point, you want to define your estimator as the argument of something, so that it depends on theta hat is not too much of a problem. The problem is that it depends on theta. So you cannot really define an estimator as minimizing this. If you want to minimize this, you need to remove the dependency in theta first. This is what we call, for example, minimax estimators. So you could define theta hat minimax by saying that what you want is, so you define it as belonging to the argument in theta hat of the max in theta of this risk. Okay, that's fine. Now you've removed the dependency in theta by taking a max. So that's one approach to frequentist statistics. That's quite ubiquitous in Valt's book. So be a minimax frequentist, be a Waldian frequentist, by considering this loss, this risk function, to be the basic object. Another thing that this risk function allows you is to define a partial order on estimators. So you could say that theta tilde is inadmissible, or I'm going to define admissible. So theta tilde is an estimator, and I'm going to define an estimator to be admissible if and only if there does not exist a theta hat such that, maybe it's better to define inadmissible, because otherwise I'm going to run into weird quantifiers. So theta tilde is inadmissible if and only if there exists a theta hat and a value of theta such that Rw of theta hat is smaller than Rw of theta tilde. And I was planning to get confused with quantifiers. There exist theta hats such that this holds for all theta. That's what being inadmissible is. And let me explain now, because I got confused and I'm probably confusing you. Being inadmissible means that there is an estimator that dominates you in the sense of this function, in the sense of having a risk function that is always smaller, always for every theta, right? So if for every value of theta, for every possible value of the parameter, my risk function is smaller than yours, then your estimator is inadmissible. You should use mine. Yep. You're absolutely right. You're absolutely right. Because otherwise theta hat and theta tilde could be the same. So there needs to be one value of theta such that this holds. So this second line is there exists theta. So for every theta, my estimator is better than yours. And there's one value of theta for which it's strictly better. So you should really use mine. There's no, yep. Yes, because otherwise my risk function could be better than yours on this particular value of theta and worse than yours on some other value. And then since we don't know the value of theta, it could be either one. There's no reason for you to really strictly prefer my estimator. So if my estimator is always better than yours, and it's strictly better than yours, at least on one value of theta, then you should prefer mine. Okay? That's what being inadmissible means. There is a theta hat such that you should prefer this theta hat if you were Wald, basically. So it's a very strong notion, but it's not very practical because it's not very usual to be able to rank two estimators using this partial order. Usually you have two estimators and there are values of theta for which one has a smaller risk than the other, and the relation is reversed for another value of theta. But definitely when an estimator is not admissible for VALD, you should drop it out. So let's see an example of an inadmissible estimator. Who knows who this guy is? I didn't. I mean, I know the name, but I had no idea he looked like this. That's Tikhonoff. So I put Tikhonoff's picture, but I should probably put someone else's. So Hull and Kenneth came up in 1974 or something with another estimator for linear regression, the ridge regression estimator. So theta hat lambda, so the argmin of y minus x theta squared plus lambda theta squared. Again, all the norms are Euclidean, and this is equal to, again, if x is full rank. Oh no, actually here you add this plus lambda I, so you don't need it anymore. Minus 1 x theta x transpose y. So this is the classical ridge regression estimator, and it's a theorem by, I think I checked yesterday, it's first time it appeared was Theobald 74, and this theorem says there exists lambda which actually depends on the true value of the parameter, such that the risk of theta hat lambda as a function is always smaller than the risk of theta hat MLE. And I've forgotten again, you need something strict. And there exists theta such that I'm pretty sure you can actually, maybe you don't need it this time because you can actually show this. It's actually strictly smaller. So one example of inadmissible estimator here would be the MLE estimator, because ridge regression, there's a small lambda that actually makes the mean square error of the ridge regression estimator smaller than that of the MLE. Okay, now in terms of, you could also derive the sampling distribution of theta hat lambda. It's a bit more painful than in the case of the MLE, but it's doable. And that's actually what Theobald does when he actually proves this. So you could use this to derive a confidence interval or a confidence region. But then again, if you're really Waldian, what you want to do for a for a confidence region, it's another action, it's another decision problem. So you would come up normally, you should come up with another loss function for deciding what your confidence region is. And you should probably not straightforward go to the sampling distribution of theta hat lambda to decide your confidence region. So I don't want to spend time on this, but that's maybe a natural remark. Okay, who knows who that last guy is? So that's Thomas Bayes. The English minister from Kent, 18th century. Not sure he can really arguably be called the first Bayesian, but it's caught up. It's actually Fischer apparently who coined the term Bayesian, and he meant it as an insult. So, and it stuck. He was really, really mean. I mean, this is maybe not his worst thing, but he wrote a note after the death of Wald. So Wald and Fischer, as you can see, like have two conflicting views on how frequentist statistics should be done. And after the death of Wald, I've read a note of Fischer that he published somewhere, sort of obituary for Wald, but the obituary is actually really mean. It's like I don't think he was I don't think he was a good mathematician, and I don't think his goals were good, and I'm not even sure he was good enough a mathematician to reach them, or something like this. So it's really like doubly mean. It's very well said. Like he puts it very elegantly, but it's very mean. He was apparently a very special person. Anyway, so let's say the fictitious Thomas Bayes. So what Bayesians would tell you, they would tell you, okay, start like Wald, define this loss function, okay, integrate it with respect to y given x and theta, but this time add another layer of expectation, an expectation with respect to theta. And now you've got a function that is independent of theta. You've got a function of theta hat, and you can minimize this. So you can define theta hat Bayes as the argmin of this expectation with respect to theta, the expectation of y given x and theta, L of theta hat. Okay? Let's look at an example of what this could actually give us. So let's say y given x and theta is still the same thing. It's still a Gaussian centered at x theta with covariance matrix sigma I squared, and assume we have a Gaussian prior here for theta. The prior is this marginal distribution over theta that I've added here by definition, and let's add something in lambda minus 2i. Okay. Question, exercise, what is theta hat Bayes in this case? This is the moment where I drink some water and I let people scribble. I don't know, is this, maybe this is obvious. I don't know if, let me see if I've calibrated. Is, for whom is this obvious? It's okay. Not too many then. All right, so let's take our pens and scribble, and I give you 2 minutes to find this one. And I go and quickly catch some water. What is that? No, I'll wait. I would pass among ranks, but with COVID, this might not be the... I'll just let you think. I've put a dot here, but it's up. This is a 0, right? I'm just putting a Gaussian prior on theta with mean 0. Yes? Yeah, let's say, thank you, Julien. So let's say let's say, note that we still take L theta theta hat. Ouais. Ah, c'est super, merci. We still take the L2 loss. All right. Any answer from people who didn't know the answer before? Nope. Maybe it's good that I maybe start with you guys then. All right, so the question was, what is theta hat base here? Let's assume sigma is 1 just for simplicity. So x theta, and I'm just going to assume identity covariance matrix for y. Okay, what are we trying to do? We're trying to minimize this loss. This loss is the integral of theta minus theta hat squared times p of y given x and theta, p of theta, dy d theta. Okay. Now, what is this product? So let's look at the log of p of y given x theta times p of theta. This log is proportional to the one who's whistling. Sorry, just turning this down. Fine. Okay, what is this log equal to? So this log is 1 over 2 times, that's the term coming from this likelihood. Okay, there's also a normalization constant in front of the Gaussian, but it's not going to depend on theta, since I just want to make a point that this product of two things is going to be proportional to a distribution in theta. And then I'm going to use the fact that if you minimize the squared expectation, the squared distance to a value with respect to, and you minimize this x taken as an expectation, it's going to be the mean of the distribution, which is the answer, which minimizes the squared deviation. So I'm just going to keep track of the terms involving theta here. So this is proportional to this term involving theta, and then there's the same thing coming from the prior. So it's going to be minus lambda divided by 2 theta squared. Okay, but this is a quadratic form. So this product of two things is actually an exponential of a quadratic form. It's actually going to be a Gaussian. So let's put it in the form of a Gaussian. So what do we have here? We have, let's do it slow. We have this, we have minus twice, and we have x theta, and we can put the, oops, what is this? Okay, did I add some extra space on the next slide? Yes, perfect. And then I'm gonna use the very bottom here. I just want to complete this and make a quadratic form out of it. So yeah, I removed the sigma squared. I decided that sigma squared was 1 up there. Up. Okay, so this is going to be a quadratic form in theta. So theta minus something. Then I already know the matrix in the middle because it's given to me by the quadratic terms. So this is going to be proportional to minus 1/2 theta minus something times this big matrix times theta minus the same something. And if you want to make the linear terms correct, you just introduce here the inverse of that matrix and x transpose y, and there's a transpose here. And the same thing goes here. And this thing is actually theta, the ridge regression estimator, if you remember the definition. This ridge regression estimator is exactly this quantity. It's exactly what you have to put here to get the right linear term. Sorry, I'm all crammed up at the bottom of my slide. But what we're doing here, let me sum up what we're doing, if I've managed to confuse you. So we are writing this integral here, the integral of theta minus theta hat squared in norm, times the likelihood times the prior, and we're integrating over y and theta. Okay, I want to recognize a distribution in the product p of theta, p of y given x theta. Okay, this is supposed to be proportional to a distribution in theta, just by Bayes' theorem. Let's look at what distribution in theta it is proportional to. So let's look at the log of this product. Just because it's 2 Gaussians, I want to take the log to be able to work with smaller quantities. And I'm writing this sign proportional to mean that I'm forgetting additional constants. Okay, and I mean constants in the plus sense. Everything that doesn't depend on theta doesn't interest me. I want to recognize a functional form in theta to say that this is a given distribution. So let's look at the first term, the first contribution coming from the likelihood. The only term that depends on theta is this quadratic form, and the term that comes from the prior is this other quadratic form. And if I put them together in the form of another quadratic form, I get what's at the bottom of that slide. Okay, which allows me to say that this product of 2 Gaussians is actually a Gaussian in disguise. Up to multiplication constant is just a Gaussian with mean the ridge regression estimator and with some covariance matrix here, XX transpose plus lambda I. Okay? Now, remember what I wanted to do was minimize this integral. And it turns out that that integral is the integral of the square distance from theta to theta hat squared times a distribution. It's the expectation of this squared distance with respect to a distribution with mean theta hat lambda. So the minimizer is actually theta hat lambda by definition of the mean. Okay, so the Bayes estimator, the Bayesian estimator in this case, is theta hat lambda, is the ridge regression estimator. Okay, so the ridge regression estimator was Bayesian. So Theta hat base, in this case, is theta hat lambda. And moreover, it's the only estimator in this augment, so theta hat base is unique, and the unique base estimator is necessarily admissible. So you can try and prove this, it's not difficult. A unique Bayesian estimator is admissible. Thus, we've actually proven that theta hat lambda is admissible. So we found an estimator that we call the Bayesian estimator by introducing a marginal distribution on theta, which we call the prior. And it turns out that this estimator is a well-known frequentist estimator in the sense of Wald, the ridge regression estimator. And this actually proves a good frequency property a good frequentist property for a theta hat lambda. So this is the first example of the interplay between Bayesian estimators and frequentist estimators. It quite often is the case, and we'll see other examples and maybe deeper results that say that being Bayesian is often a good way to be a good Waldian frequentist. And we'll see a theorem that's called the complete class theorem that essentially says that this is the only way to be a good Waldian frequentist. So you could be willing to be a Bayesian just because you want to be a good frequentist. Okay. So let's try to take these examples one step further in terms of notation. So it's going to get notation heavy, but you'll see that there's a reward to it when we get to the why being Bayesian part, because we'll be able to come up with sufficient conditions under which this is the right way to make decisions under uncertainty. But the price to pay is that we have to introduce this new layer of formalism, which is the formalism of Wald in his book. Actually according to, it's a slight modification of the Wald formalism according to Savage, which we'll meet later on. So, when you want to describe a decision problem under uncertainty, like the estimation of a theta or the prediction of a label, be it in classification or regression, what you need, according to Wald, is four things. You need a state space. The state space S is every quantity you need to consider to make your decision. You need a set of actions. A set of actions is a set of functions from the states to some abstract reward space, Z. Z is this reward space. It encodes how you feel about a particular action, about having picked action A. So let's see an example right now before this gets too abstract. We had regression. Our state space was theta. We had data y1n, x1n, and y1n. Those were all the variables in our problem. We had the features, x1 up until xn, the labels y1 until yn, and we had a theta. This forms my state. So this is what I call little s. I will always call little s states. So the state space in this case is theta times x to the n times y to the n. If I denote by calligraphic x and y, the spaces in which x and y live. Okay, this is the example of a state space in the case of linear regression, for example. Actions. We had actions in the case when we wanted to estimate theta. Our actions are functions from states. So a function from S, that is a function from theta, x1n, y1n. And what were our actions? Our actions were estimators. So they were functions of the observed data that we're trying to predict theta. So we could say that our action was, let's say it's indexed by, let me call it G. So G is my predictor. It's G of x1n, y1n. And I can take minus theta. For example, that's my action. I chose here to have a reward space Z, which is theta. And I use the function G that maps data to a candidate theta. So that's my estimator, right? This is what I implement. This is theta hat of the data. I call it G because I will try to keep calling it G, whatever the problem be, estimation or classification or prediction or anything. Is it clear, or am I adding confusion to the confusion? Don't hesitate to stop me. Okay. So I have this predictor. It's predicting a value of theta. It's called G. It uses the data, and I decide to take as an action the choice of a G. So my action is labeled by this function G, and my action as a result is the result of my action is the difference between this prediction and the value of theta that is in the state. So my reward space here is theta. Okay, it's where the range of the actions lie. And you need a loss function which encodes how much you would suffer from picking action A in state S. Yes?
So if I understand correctly, your action is not G, choosing G?
Yeah. Yeah. It's a bit, so it's going to be a bit weird at first, but I want to keep actions to be functions of the states. So the trick is to then label the action with the actual thing that you think of choosing. So either the 0, 1 label if you are in classification, and here it's always going to be labeled by my predictor, and my action will be choosing my predictor. This is not very conventional today in textbooks, but it's what you would find in Savage's book, for example. And it's going to be useful if I want to be compatible with tomorrow's talk, where I'll probably cover Savage if I don't have to talk about it today. So loss function. The loss function is encoding how much I suffer from picking action A in state S. And so far, my loss function was exactly G of x1n, y1n minus theta squared. This is what we've used. Okay? You can see that it's very non-identifiable. I could come up with this, I could model the same decision problem with different choices for my actions and my reward space. There's a lot of redundancy here. But for complex problems, you actually need all of these. Okay. So let's see another example. Classification, my state space, again, all the variables that I need. So depending on whether I want to model, here I've added here data. There's a test point, there's a test X, and it's test label Y. I could add theta if I wanted to actually parameterize my G's. Here my Z is going to be 0, 1. My reward space is going to be binary. And my action, again, is going to be, all my actions are going to be labeled by a small g, which is going to be my classifier. It's my predictor. My predictor is a function g of x, the new features, but also of the training set, right? My goal is to output an algorithm. An algorithm is something that takes as input a training set and a new instance of the features to which we want to attach a label. So my action here is going to be a function that takes S and that outputs 1 if and only if Y is different from the prediction of G at X when trained on the data set. Okay, and it's going to be 0 if the labels are equal. And my loss is going to be exactly this indicator. That's the 0, 1 loss. That's a choice again. All of this is a choice. The important choice here being the loss, because that's really up to you how much you suffer from misclassifying something. We'll see in a moment that you could have an asymmetric loss here as well. You could decide that you don't suffer the same thing when you misclassify a 0 than when you misclassify a 1. Okay? So that's an example of another decision problem that we've mapped into Valt's framework. And what you can already do with this without even being Bayesian is pack bounds. PAC stands for probably approximately correct. And it's the archetype of results in statistical learning theory. In statistical learning theory, when you see a classification problem, you think of it in terms of a Wald decision problem, and you want to guarantee something like this. You want to guarantee that the generalization error of your classifier is smaller than epsilon. And you want to guarantee this, you want to give a frequentist guarantee about this, so you want to give a guarantee under the data generating mechanism here. And you want to guarantee that with large probability under the data generating mechanism, the expected loss is small. Okay? And maybe this is only true for n large enough, so you want to be able to characterize how this large enough n actually behaves in terms of delta and epsilon, the two parameters here. Okay, so that's called the PAC bound. You can go and check out this. It's a good entry point into statistical learning theory. So, okay, classification as a decision problem, we've modeled it. So now I want to introduce you to subjective expected utility, which is just the abstract way of stating what we've been doing with these small examples where I showed you the heads of Fischer and Bayes. Now that we've introduced the whole formalism, the subjective expected utility principle is really, to me, what unifies all Bayesians. Every Bayesian somewhere behind his head has this subjective expected utility, maybe 95% of Bayesians, which is already enough. So you choose a state space, you choose a reward space, you choose an action space, you choose a loss function. Then you choose a distribution P over the state space. And remember, the state space contains any variable in your problem, whether it's variables that you can think of being attached to some aleatory uncertainty like the roll of a die, or whether it's the propensity of the die to fall on a given face, that's completely irrelevant. You should put a probability over everything. Okay? Aleatory or epistemic or anything, you just put a probability over every parameter, every variable in your state space. And then you take the corresponding Bayes action, okay, which is 1 here. The Bayes action is just the augment of this expectation under this distribution that you've put over states of your loss function. And then if you remember, when we were completing the squares and deriving the estimator that corresponded to a Gaussian prior in linear regression, we actually did what's in this green box here. So what I'm using the towering property of the expectation here, and I'm taking out an expectation over what's actually going to be observed. So now I'm partitioning my states into a part that I'm going to observe, because I actually think that this is going to be an inference problem, this is going to be a statistics problem, there's going to be some data, there's going to be parts of my state that I actually think as observed, and I partition them as observed and unobserved, and I just use this towering property of the expectation to define my Bayes action A star. Okay, for now I've done nothing. The important stuff comes next. In every example that I've shown you so far, my G, the G, remember, was either the estimator of theta or the predictor in classification. So it was always a function of the data that was outputting the quantity of interest. What you might have taken maybe as an action, this quantity of interest, either the theta or the y in classification. But here it is my G that is taking into account, taking as an input the observed data and outputting the quantity of interest. So assume my action set is actually a set of actions labeled by such G's, which are functions of the observed variables. Then to minimize 1, it is actually equivalent for me to pick my A star as a function of these observed variables, and to always minimize what's inside the expectation here. What I'm saying is, since I'm picking an A, and equivalently I'm picking a G, and G is a function of S ops, all I should do is for each value of S ops, I should pick the G that minimizes this inside this inner expectation. And if I do this, I will have minimized the overall expectation. Okay? So here I'm explaining how to pick the Bayes action using what's called the decision rule, a function that maps the observed variables in a statistical decision problem to an action. And my decision rule is to take the argmin of this posterior expected loss that I consider as a function of S ops, the observed part of my states. Okay? This is just a complicated way of saying what we all do. We are minimizing posterior expectations of losses. Okay? And this is just me reformulating it in a very abscons way, but you'll see with when we talk about foundations why there's actually an interest in introducing all this formalism. I already think that is nice because it's encapsulating all of Bayesian learning in one line, basically. It's minimizing posterior expected losses. And whatever the decision problem, whatever the statistical problem that you face, it can be a ranking, it can be clustering, it can be classification, multi-class classification with asymmetric losses, like anything, any decision problem under uncertainty can be mapped. If you give me your 4 items of the Val description, your A, your L, your S, and your Z, I can give you the Bayes action. And this is already something I think that's very unifying and very auditable. It's something that you can easily communicate to people. There's nothing ad hoc in a Bayesian estimator. It's always the same line that sums up every application of Bayes. So let's now revisit the previous examples using this corollary that I have just shown you. And what I want to arrive at in the next 2 slides, what I want to arrive at is I want to express this G star, this A star, this Bayes action. I want to express it using integrals with respect to a distribution in theta. Just like what we did when we derived the Bayesian estimator for linear regression, we ended up saying, oh, but the Bayesian estimator is just the mean of some distribution, which I didn't say, but was actually the posterior distribution over theta. So we expressed it as an integral over a distribution in theta, and this is what I want to do for at least 2 different tasks. So point estimates. So this is actually what we've already done. The base action, G star or AG star, minimizes the expectation we set of, so the unknown, what is unknown here? Theta only. And what is known? Y1n. And this is our loss. So that's the, I should actually know G star of S, G star of Y1n, just for consistency. Okay, we should take it to be in the argmin of this. And the argmin of this is by definition the mean of theta given y1n. Right? It's the mean of that distribution by definition of the mean. Yep. Sorry, can you?
How is it that the loss does not depend on the?
So the loss does not depend. The loss depends here. So the form of the loss does not depend on the state. Here it depends on theta and it depends on y1n. But it is true that we've decided that we would, for example, suffer the same thing when theta is 1 and theta is 3, and g is away from one of these two values. That is true. This is an implicit assumption. You could make the loss depend on the state in a more, let me write this. Voilà, right. So if you seem to have looked carefully, every time I've defined the loss in this talk, it was actually only a function of A of S. And it was actually minus a function that I will call in the next talk the utility of A of S. And I've defined my actions such that the output of the action, A of S, was all that I needed to compute my loss. So for example, in regression, A of S was theta minus G of Y1S. And again, S is theta and Y1 up into Yn. So the action, the loss depends on S only through the image of S through A. If what you're asking is whether we could actually put an S here, make this U function depend on S, that's a very good question. It's not possible according to Savage. So we'll see in the foundational part of the lecture that if you abide by some axioms on how to pick actions, it is forbidden to make the utility depend on states. Here I've been very careful in making it not depend on the state because I want to be retro-compatible with Savage, but it's a very good question. Why is it in linear regression, or in estimation even, that we want to suffer the same thing when we miss theta by 1 and theta is 0, than when we miss theta by 1 and theta is 1000? Maybe we don't want to suffer the same thing. Maybe we want this amount of suffering to depend on theta. And then if we decide to do this, then we're going to make the loss state dependent. And it's a perfectly reasonable thing to do. We'll see that maybe the dominating set of axioms behind Bayesian stats forbids this. But it's something that you could do, that you might want to do. And there's sets of axioms, there's Bayesian frameworks, especially in econometrics, where people are attached to making the loss depend on the state. Their basic example is they have prices in their states, and the prices depend on exchange rates. And basically the loss function, at some point the real price to you is going to be a function of the exchange rate at some point, and the exchange rate is some part of the state. So they want the loss function to be state dependent, because the loss function is going to take some part of the states to compute prices, and it's going to use other part of the states to compute exchange rates. But even in plain estimation, it could be irrelevant. I don't know why we basically assume that we suffer the same thing. It's actually a weird assumption to come up with with a loss that only depends on the difference between the two and not the value of theta. Was that your question? Yeah. It's a subtle question, actually. I was not aware before I looked into Savage that it was it's basically not covered by Savage's actions. You don't just do that by changing the action. So you could do that by changing the action, but then, so you could, for example, say the action contains this and theta, and then you could use that part. But then you're going to be trapped by another piece of Savage, because Savage is going to require you to have constant actions to be able to rank constant actions. And if you only have this, you have no constant actions anymore. And your constant actions should always be part of your actions. So it's a tricky part of Savage's proof, and it's really the whole of the probability measure will be built using these constant actions. So you're actually a bit tied into as to how you define your actions. Yep. Yes. Yes, you're right. And then what is the problem? Let me think about this one, but I think it won't fit Savage's framework either. So let me make a note to come back at it. Well, I'll remember it. I don't think it will fit Savage's framework either. Because it's one famous thing that Savage's framework like precludes the fact that you can have this state-dependent loss in estimation, for example. All right, so okay, so that gave us the Bayes decision as the mean of the posterior distribution. Let me write it. So this is just going to be the mean of the posterior distribution of theta. Now, if you want to do credible intervals, so remember in the first paper, the physics paper that I had shown you on the first Virgo and LIGO joint event, they had credible intervals on the masses of their black holes. So how do you come up with a credible interval? What's an interval that you communicate in a scientific paper if you're a Bayesian? One possibility is again to translate this into a decision problem. I have states, data, a parameter. Z is my parameter. My actions are again, what do I need to know to judge the quality of an interval? So that's again what we need to think as the output of an action. We need to know whether theta is in the interval, right? G is always this measurable function of the data, and it's outputting the quantity of interest. The quantity of interest here is an interval or a region if theta is multidimensional. So G, think of G of y1n as a subset of theta. I need to know whether theta is in there, right, to judge the quality of a credible region or of an uncertainty quantifying region, since I haven't named it credible region yet, but judge the quality of an action that is a region and supposed to quantify my uncertainty on the parameter, I should at least know whether the parameter is in there. Of course, if you only take this into account, you can already have the intuition that in the end, the optimal region that you're going to select is going to be the whole space theta, because it always contains every value of theta. So actually what you have in mind as a statistician, as a good uncertainty quantifying region, is a small region. You want it to be small as possible, and you want it to contain theta. So I'm gonna keep the size, say the Lebesgue measure of that. I'm gonna assume that G takes values in measurable sets, and I'm gonna take the Lebesgue measure of this set here. And my loss function to the statistician, the loss function of choosing an uncertainty quantifying region is could be like a 0-1 loss, whether theta is in the region. That's reasonable, plus some penalty, because I don't know how to compare the two, times the size of the region that I'm outputting, the interval if it's 1D. Okay, and I need to choose this gamma. It's up to me, but you'll see that it's not crucial to define it, because so when I want to define my base action, what I do is, again, I minimize the expectation of S unknown given S known. And I have my loss function. So there's the indicator of theta being in G of Y 1n plus gamma times the size of G. And the expectation only goes until here because the rest is a constant. So what we want is we want a region G that has a big coverage, that covers a big part of the posterior. So it needs to have a large mass under the posterior, is what I'm saying. That's the first part of this objective. And it needs to be small. We usually don't define gamma, and what we do is we take our posterior. Let's say theta is one-dimensional. We take our posterior and we find a way to design a region that has more than some pre-specified level, say 95% of the mass. So if 95% of the mass is contained between these two regions, these two lines, I could define G as being that interval. Of course, this is far from unique. There's an infinite number of credible regions that I could define like this. I could decide to have them semi-infinite to the left and then move my threshold up until I have 95% of the mass. Semi-infinite to the right, move my threshold to the left, and I was moving it to the right before. I could decide to center them at the mean of the posterior distribution and then to extend it symmetrically on each side up until covering 95% of the mass. It's up to you to decide. But it's always some kind of heuristic way of minimizing this in G. All we do in every package, like if you're using PyMC or Pyro or any probabilistic programming package or project that is out there, when you ask it for a credible region, implements some sort of heuristic to minimize this objective, denoted by a sharp sign. And it's optimized. So we never really solve this. We usually solve this by hand, by finding a homemade definition of a region G of Y1n that covers a pre-specified amount of mass of the posterior. Okay? But again, the only computation that's involved is integrals with respect to the posterior. So again, we'll need integrals with respect to the posterior. Classification is the same thing. So expectation of unknown given known. So the unknown thing is here theta, and I don't know y, and I know my data set, and I've chosen the 0, 1 loss here. And I'm just going to drop the dependency of G on the training set just for notational convenience. But let me use the towering property of the expectation again. Take an expectation with respect to the posterior. And this is the expectation of y given the rest. But remember the structure of the PGM, of the probabilistic graphical model? We had xi, yi, big plate. There's a theta parameter that comes in to define the conditional of y given theta and x. And it's the same theta that you use to define the conditional of your new y given your new x. But so y, conditional on x and theta, its parents, is independent of the training set. So this is actually only y given x and theta. Okay? This is equal to expectation of theta, knowing everything. And then you have, we're just going to write in full this expectation. So it's the probability that g of x, the probability that y equals 1 given x and theta times the indicator that g of x is not 1 plus the probability that y is equal to 0 times the integral of g of x is not 0. And you can guess from this that the g of star of x, this time I'm going to write the dependency in full, is actually the indicator of whether the posterior expectation, again a posterior expectation, of this predictive distribution is larger than a half. So this is the event. And let me just add a point of vocab. This thing here is called the posterior predictive distribution. So the probability of y given x and theta, if you average it over the thetas, over a theta with respect to the posterior distribution, it's called the posterior predictive, and it's exactly the quantity that's at play here. It's the quantity that you need to compare to 1/2 to know whether you want to classify your point as 1 or not. Indeed, let me choose another color. If the expectation here, if the expectation here of this thing is really large, then you want g of x to be 1 so as to make this indicator to 0, to be 0. Because you don't want to suffer that term, you want to suffer the other one. Because if this one is large, then this one is small. And vice versa. If the other one is small, you want to suffer the first one. And when does the threshold happen? Exactly at 1/2. If you had decided to put another loss function here, but you had to decide to put alpha times the indicator that y is not the right prediction, but you want to weight differently the errors of misclassifying a 0 and misclassifying a 1. Then you'll end up with an alpha here and a beta there. And you'll have to add the, oh, sorry. If you do this, I'll let you do as an exercise, that you end up with exactly the same decision, except that you'll compare here to a threshold that's alpha divided by alpha plus beta. Right? Alpha is the cost of misclassifying a 0. If it's small, then you want to always predict 1, because misclassifying a 0 doesn't cost much. So the threshold is very low with respect to which you compare your posterior posterior predictive in order to decide whether to label a point as 1. So it's the message here is that this subjective expected utility formally is a very powerful tool to model any decision problem under uncertainty, whether the cost is asymmetric, whether you have multiple classes, whether you want to do ranking or anything. It's very automatic, right? It's a little formal, but once you've formalized it, the rest is just writing. There's no choice. And this is what I like in the Bayesian framework, is that unlike what people might say, because there's difficulties in specifying this joint distribution and especially the prior parts, the whole building is actually quite mechanic. And once you've specified your loss function and your actions, no one really complain. Loss functions, you have to talk to your client, or you have to talk to the person you're doing stats for. You have to talk with him to decide the right loss function. But once you agree with this, and you agree with, say, a dependency structure for P, the places where things are ad hoc are quite limited. And I think overall, it's one of the most objective ways of treating a problem of decision under uncertainty than to treat it as a Bayesian problem. Well, I'll finish with this slide. So this is just the posterior expected loss. Minimize the posterior expected loss. Sums up pretty much every Bayesian endeavor. So it's what you should have in mind. And as we've seen, it often boils down to computing integrals with respect to theta. And the measure with respect to which we want to compute these integrals is usually a posterior distribution. So this is summarized by this one line. And in a sense, all of Bayesian learning or statistics is there. It's one line. It's always the same thing. It's very mechanic. Choosing at least the dependencies in pi is often relatively natural, is what I was saying. We'll see tomorrow that choosing the prior can be difficult, and it's especially the one part that is difficult to settle if you work with physicists or biologists, for example. But there are ways to try to at least partially automatize this, but it depends on which philosophical interpretation you actually give to this subjective expected utility. And we'll see tomorrow that there's actually a great number of varieties of Bayesians. One Bayesian even joked that it was like more than 40,000 of them, depending on how you justify the subjective expected utility, how you interpret it, and how you implement it. Whether you turn it to a maximization problem because you're working with images and inverse problems and you have powerful optimization tools at hand, and you certainly don't want to compute an expectation because it's going to take years, but you know how to optimize that function, that's in your integral. That's one way of looking at it. Or maybe you want to integrate everything and you're willing to tune your Hamiltonian Monte Carlo very finely to actually optimize, integrate over all these variables. So that's what I mean by the differences in ways to implement that principle. And I forgot what the last line was, but it's going to be the last line, and we're going to discuss it tomorrow anyway. Of course, yeah, depending on what choices you make on this first bullet, it gives you different degrees of freedom, especially for the choice of prior, which we'll discuss tomorrow. All right, thanks for your attention.